Okay, this is Paul Guyer, and I will be your presenter today for this PDH, pardon me, PDS webinar, PDH source webinar, an introduction to noise control in buildings. A couple of housekeeping items to get things started here. The way we proceed with the webinars is I press on with the presentation for 50 minutes. Then we take a 10-minute break, come back, do another 50 minutes, 10 minutes, keep going through that cycle. And that we'll be doing. This is, of course, an interactive webinar. Questions and comments are welcome and encouraged. We've got two ways of communicating. One is that you can just speak right up on the audio stream, and the other is the little chat box where you can type in a question, and I'll try to keep an eye on that as we move along. Occasionally we have audio difficulties, feedback or echoes, things like that. If that happens, I may need to mute one or more of your audio streams to make that go away, in which case you would just have the chat box to communicate with. However, everything sounds good right now, so I think we'll press on then with an introduction to noise control in buildings. Want to place emphasis on a couple of words in the title. The first one is introduction, because that's what this is. This is not for targeted, this webinar is not targeted at engineers that have been dealing with noise control and acoustics for many years, and that you're looking for a very nitty-gritty technical discussion. That's not what this is. This is targeted at all of the members of the building design team, and the assumption is that you're passingly familiar that in building design there can be noise control issues, and hopefully this will give you something to address those kinds of projects when they come forward in the future. Also, I would put emphasis on the words in buildings, because that's what we'll be talking about today almost exclusively. There can be other situations where noise control is an issue, noise control in the exterior environment as an example, but we'll be talking primarily about noise control inside buildings. Okay. There we go. This is kind of what I'll be talking about today. The chapters in the book, if you will. I'll talk a little bit about the fundamentals of acoustics, kind of the underlying physics, if you will. Chapter 3, noise criteria. In other words, this is your target for in building design. The criteria that you establish for the different spaces in your building. And that criteria is driven by the human activity that's going on in the individual spaces. Are people trying to sleep? Are they working in an office? Are they in a shop environment? so on and so forth. So noise criteria, that's your target for your design of the building. Sound distribution indoors, a little bit picture that I kind of draw of how the sound moves from the source of the sound to the receiving room. And I'll tend to generally talk in terms of a source room and a receiving room. The source room is the noisy room. Somebody's making noise in there. The receiving room is the one where you're trying to design for a particular sound or noise environment. By the way, the words sound and noise both sound alike, kind of alike, but actually noise is a subset of sound. Noise is unwanted sound. And so what we're concerned with is noise control. Sound isolation between rooms. How do you control or mitigate the sound that's being generated in the source room so that it's not bothering people in the receiving room? Well, fundamentally, what you're doing is constructing barriers, walls, ceilings, floors. There are also in building design some other considerations. One is the air conditioning system and the duct work that's running around the building, and it can be a pretty substantive conduit for noise getting from one room to another. To the extent that we have time, I'll talk a little bit about sound propagation outdoors. That's where the source of the sound is outside the building, and maybe the receiver is inside the building, or maybe the receiver is outside the building. And I'll have a few comments on that. Airborne sound control, we won't be able to get into that. That is talking about things that you may need to do other than as part of the building design. Things like personal protective equipment, earmuffs. If you can't design in a satisfactory noise environment, people may have to utilize some personal protective equipment because prolonged exposure to high noise environments can result over time in hearing damage. Here, by way of introduction, is just a little bit about me and what I've been doing for the last few decades. For 35 years, I was what I characterize as a straight-ahead building designer, designing, cranking out drawings and specifications for the construction of buildings and a fairly broad spectrum of infrastructure features. And I did not spend 35 years doing nothing but acoustic projects. It just happened that along the way, I would get these projects where noise control was a consideration, and that's where I picked up a bit of understanding of the problems here. So, and then after that, for what it's worth, I was out of the building design business And for 9 years, I was a in the what might be called the public policy business, where I was a principal staff advisor to the California legislature on infrastructure and capital outlay issues. And occasionally there was a need to explain noise control and things like that to the members of the legislature. Okay, so here we go. A point to begin with, I think, is that noise begins when something's vibrating, essentially. It may be a string on a violin. It may be vocal cords, somebody talking or singing or yelling. And it may be a piece of equipment that's making noise, fans in fan rooms, things like that. And the picture I like to draw is that essentially with sound, it's what it is it's vibrational energy in air molecules. You have a source room where the noise is being generated. You have the receiving room where you want it to be quiet. And something starts vibrating in the source room like a violin string, and the molecules in the solid string begin to vibrate, if you will, with acoustical energy. And you can visualize it as a sinusoidal curve, up and down, up and down, up and down. And the thing that's vibrating impacts air molecules in the source room. Those air molecules are set into a higher level of vibrational or acoustic energy. And one molecule bangs into another, and in a line, they are contacting each other until finally they get over and impact the wall, the barrier that's between the source room and the receiving room. And then the solid material molecules in the wall structure begin to vibrate, if you will, and that vibration energy is transmitted then to the air molecules in the receiving room. The chain of interaction between the molecules continues until it reaches the eardrum of the human in the room. And then the eardrum is impacted with this vibrational energy. And this vibration, if you will, is what the ear and the brain perceive as sound. A companion phenomena to sound is vibrations. They both start in a source room with something vibrating. It might be a violin string. It might be a fan in a fan room spinning around and bouncing around and making noise. And the kind of the distinction between the sound and the vibrations is the sound tends to be largely a through the air type phenomena, not exclusively, but largely. Whereas vibrational energy is primarily transmitted through the structure of the building, the beams and the columns and the decks and so on and so forth. And then over in the receiving room, the human perceives the sound through his ear, his or her ear. And then in the receiving room, the receiver perceives the vibrations through his fingers and toes. The floor is vibrating. But their companion, and the sound vibrations tend to be of a higher frequency than the vibrational frequency. So they're different in the way they are transmitted, and they are different in the way they are perceived, but they are companions. They begin with something vibrating in the source room. Okay. And okay, now here are some concepts to keep in mind about acoustics and sound. And again, the best way to get a handle on these is to think of them in terms of a sinusoidal wave. The first of these qualities of sound is level or magnitude: loud sound, quiet sound. So perceive a sinusoidal curve with a high magnitude of amplitude, up and down and up and down and up and down, and with that kind of a vibrational energy. That is a loud sound. If the amplitude of the vibrations is small, just up a little bit, down a little bit, up a little bit, down a little bit, that is a quiet sound. So level or magnitude, and loud sounds, quiet sounds. And the next quality that is, if I get my, is the frequency of the vibration, if you will, or its spectral content. So frequency, again, thinking of the picture of a sinusoidal curve, if it's going up and down and up and down very fast, that is a high-pitched sound. And if it's the frequency is slow, up, down, up, down, up, down, that is a low bass type sound. And a point that goes along with frequency is spectral content. In other words, in the real world, you never hear a pure tone that just is of one magnitude and of one frequency. What you're hearing is bundles of sounds with a lot of different magnitudes and frequencies. And when I'm talking here, there are air molecules, if you will, that have high magnitudes and low magnitudes, high frequencies and low frequencies. So spectral content, and the fact that we can generate and perceive sound this way is what allows us to have speech and music and things like that. A third quality that is important to perceive is the time or temporal variations. In other words, at one instant in time, you are perceiving, I am generating, and you are perceiving air molecules with one family of magnitudes and frequencies, and then an instant later, it's something different. So it's constantly changing the levels or magnitudes of the oscillations and the frequency and spectral content. Okay, that's all very interesting. So how do we measure or quantify sound? Well, the unit of sounds is the decibel, dB. And it is defined by equation 2(1), which you see here. The decibels is equal to 10 times the log of P1 over P2. P1 is the sound power or sound pressure that is being perceived or either generated or perceived by the receiver, the actual sound pressure or sound power. P2 is a reference sound power, and this sound power is that which is just barely perceivable by a young, healthy human ear. So it's the ratio of the sound power perceived to a reference pressure sound power, which is that which is just barely perceivable times the by the young healthy human ear. So equation 2(1) is the definition of the decibel. And let's look at a couple of characteristics of decibels. You might say, okay, I'm in the source room and I have 2 point sources of sound that are generating different decibel levels. And I want to add them together to know what I will be perceiving as the receiver. And hang on just a minute, I want to play with my controls for just a second. First of all, this is not something that you'll encounter a need to do this, to add 2 sound levels together in building design. It just doesn't crop up. To give you a feel for what you would perceive when if you had 2 decibel sources, is that if they, as this table indicates, if they differed, the 2 sources by 0 to 1 decibel, the resultant sound that would be perceived would be equal to approximately 3 decibels higher than the highest value. If the 2 decibels values being generated differ by 2 to 3 decibels, the combination of them would be perceived as about 2 decibels above the higher level, and so on and so forth. And as you increase the difference between the 2 sources to 10 decibels or more, what you would perceive is a sound that is the same as the highest of the 2 sounds. In other words, you would add nothing to the higher of the 2 sounds. And this seems a little counterintuitive, but when you stop and think about it, what it is as the different sounds, the high sound and the low sound increases, you get to the point where the higher sound level is just overpowering the lesser of the two, and all you're perceiving is the higher of the two sound levels. So if you ever did have to add two or more sound levels together, you would use equation 2, 10 times the log of the quantity that you see there. And if the sound levels of all of the various sources you are hearing was the same, then equation 2, reduces to equation 2, 3. But again, you'll almost never have occasion to want to do this in routine building design. Now, the one area in building design where things get fairly complex and you may need to do these kinds of calculations is if you have a space in a building like a concert hall or a lecture hall, because here the source of the sound and the receiver of the sound are in the same space, in the same room. The violin player's up on the stage playing the violin. The receiver is somebody sitting out in the audience. And the challenge in these spaces is the fidelity of the sound that is perceived by the receiver, because the person sitting out there in the audience wants to hear the sound exactly as it is being produced by the source, the violin player, up on the stage. And the challenge here is in these kinds of spaces, concerts halls, lecture halls, is that the source is producing a sound, and it has a three-dimensional pattern to it. In other words, there are these sound vectors that are shooting off in all 360 degrees, three-dimensional pattern. Those sound vectors that some of them will go directly from the source to the receiver sitting out in the audience, but there will be others that will shoot off and bang into the walls or the ceilings or the floors, and then they ricochet off, and some of them will then be perceived by the receiver out in the audience. And this is how you get echoes and distortions and things like that. And that's what you need to avoid in these kind of spaces. Lecture halls, concert halls, music recital halls. If you have these kinds of spaces in your building, you should retain an experienced acoustical consultant to design the interior of these spaces. For one thing, these ways of managing the sound in these kinds of spaces has largely been developed by trial and error over centuries. We did thus and so at La Scala in Italy, and it worked. Let's do the same thing here. These kinds of spaces, lecture halls, concert halls, you need this special expertise. Okay. Now, that was talking a little bit about addition of two sounds sources and what is the resultant that the receiver perceives. You could also ask the question, well, what about decibel subtraction? I have two sources of sound with different decibel levels being generated, and I turn one of them off, and how does that subtraction change for the receiver? Well, equation 2.4 is the one that you would use if you wanted to do that decibel subtraction. Again, highly unlikely that you're going to have occasion to do this in the vast majority of building design projects. And if you wanted to, for whatever reason, take an average of several decibel sources, you would combine them to get an average using equation 2.5. Okay, sound pressure level. Now, this is important because this is what the eardrum perceives, is pressure on the eardrum. It is usually represented in formulas by L sub P and in text by SPL. And the sound pressure level in decibels is defined by equation 2.6, 10 times the log of the quantity P divided by P ref. P is the sound pressure actually being perceived. P reference is the reference pressure, sound pressure, which is just barely perceivable by a young, healthy ear. And equation 2.6 can also be written as equation 2.7. Okay, so this reference pressure then, that's just barely perceivable by the young, healthy human ear. What is that pressure? Well, it has been determined by the profession over many years to be 20 micropascals. So that is the sound pressure that is just barely perceivable by the young, healthy human ear. So that is 0 decibels then. Okay, now let's see. The sound power level is the absolute measure of the quantity of an acoustical energy that is produced by a sound source, usually abbreviated in formulas L sub W and in text PWL. And it is defined by equation 2.8, where P is the sound power being perceived, either being generated or perceived, and P sub reference is the sound power level that is just barely perceivable by the young, healthy human ear. And what is that? Well, it has been determined by the profession over many decades to be 10 to the minus 12 watts. And so that's the sound power level that is just barely perceivable by the young, healthy human ear. a point of somewhat of information is that sound power level cannot be measured directly. And this is because you have a point source of producing a sound, but it's radiating out with these sound vectors of different magnitudes in different directions in a 360-degree three-dimensional environment. And there's just no way to construct a sound power meter to capture all of those vectors. Just a little piece of information. It's not something you can measure. Okay, now sound intensity is the sound power per unit area. And so this would be, as an example, the sound intensity being impacting, if you will, the barrier between the noisy room, the source room, and the receiving room. And the definition of sound intensity is by question 2.9. Okay, now let's, there are quite a few slides here in this presentation, so we have to skip over some of them, but this is a good reason for you to get a copy of these slides from PDH Source. This is not a design manual or a text or anything like that, but it does have some pretty good information on it. Okay, let's keep now. Let's move along and briefly offer a couple comments about vibrations, because again, vibrations are the companion of sound. The vibration level is characterized in decibels and is calculated by equation 213. And there's more discussion here of vibrations than we have the opportunity to get into. So now let's talk about frequency, and this is important as far as building design and people is concerned, because the human ear is only sensitive to sound roughly between 50 and 15,000 hertz. 15,000 hertz is the high end of the perceived part of the sound spectrum. That's a very high-pitched hissing type noise. 50 hertz is a very low rumbling type of a sound. So if the sound that's being generated is between 50 hertz cycles and 15,000 hertz, the human ear will perceive it. However, within that part of the frequency spectrum, the subpart between about 500 and 5,000 hertz is where the human ear is particularly sensitive to sounds in this frequency range. Below 500 hertz, in other words, between 550 hertz, those are the very low rumbling type sounds. The human ear, yes, it can perceive them, but the ear and the brain just aren't really too concerned about sounds at that those low frequencies. From 5,000 up to 15,000 hertz, these are high-pitched sounds, and but again, the human ear can perceive them, but it isn't too concerned about them. So the human ear is only concerned or responsive to sound more or less in the 500 to 5,000 hertz range. And this is important to keep in mind. The unit, of course, of frequency is the hertz, cycles per second. And the frequencies are further divided into octaves, which you see here. And this is not something that in run-of-the-mill building design you're going to get too excited about. It may be important, again, if you have a concert hall or recital hall type of environment. And so your acoustic consultant will be concerned about the octaves. But for what it's worth, just so that you get a picture, this table shows the octave bands as they have been defined. At the bottom of the scale, and the top of the table, the octave band from 11 to 22 is the center of that is 16 hertz, and that is called the 16 octave band. And then moving down the table, you get to the high end of the spectrum, and the highest octave band that is defined is 11,360 to 22,720, and it's centered at 16,000 hertz. And that is a very high-pitched sound. And then these octave bands, for reasons that we're not really concerned with, they are further subdivided into thirds, as indicated in the last three columns. So be aware of this is what an octave is, but in building design, you're unlikely to be concerned about it. Okay, now let's get into what do you do? You've got a building, you've got a noisy room, and you want it, and you've got a room that you want to be quiet. What's the first thing you do is field work? Well, it's to go into the source room or sound level meter, which is usually a handheld device that looks about like what you see here. And the sound level meter has two dials on it. And one of them has three positions, or knobs rather, not dials, knobs. Three positions on it labeled A, B, and C, and a second knob that has two positions labeled fast and slow. And then there is a dial that you can read, a needle that shows the sound power that the meter is perceiving. And the first of these two knobs on your sound level meter, when you're going to take field measurements, has these three settings, A, B, and C, and they are represented here on this figure 2.2. And they represent the fact that the sound level meters will, depending upon the setting, will filter out or discard or not record certain sound that is being perceived. Like the A curve that you see here, this corresponds to the A curve on the um, this knob. And so you see that between about 500 hertz and 5,000 hertz, the sound level meter records and displays just about everything that it perceives. Uh, but when you get below 500 hertz or above about 5,000 hertz, you see that the meter is constructed uh, such that it discards and does not record or display uh, some of the sound at those lower or higher frequencies. And that's because the meter is constructed on the A setting to mimic as closely as it can be mimicked the sensitivity of the human ear. Again, uh, just primarily sensitive in the 105 range. So setting this knob, this ABC knob on the A setting means that the sound level meter is going to perceive sound uh, roughly the way the human ear perceives sound. The B and C settings are different. They do not discard as much of the low frequency sounds, and uh, they might be used more when dealing with machine noise in an industrial environment, but we won't go into that. But so this knob on your sound level meter, you set it on the A level, and then that means the sound meter is going to be mimicking the human ear. Let's see now. I'm looking at the clock here, and I've got 10 minutes before the hour. Let's take our first 10-minute break now and come back on the hour, and we'll pick up here, and we'll move into more of what you do in the design of the building to manage sound and noise. So let's take a 10-minute break and come back on the hour, and we'll pick up here. So I'll see you in 10 minutes. Okay, this is Paul Guyer and I'm back. So you're doing your field work, measuring the sound in the source room. You've walked in with your sound level meter and you've set the ABC dial on the A setting. Now the other knob is the fast slow setting. And this is the sampling rate, the rate at which the sound level meter samples the sound. On the fast setting, it samples the sound 8 times per second. On the slow setting, it samples the sound once per second. And the reason you have this sampling is because if you didn't have sampling, if you just had continuous display of the sound, the needle on the sound level meter would just be a blur. And even on the fast sampling rate, 8 times per second, it's still not practical for the kind of work we're talking about doing. So you would set the sampling rate on the slow sampling rate, one where the sound is sampled by the meter once per second. There is a second sampling rate that comes into play here, and this is your sampling rate. Frequently, you look down at the meter and record what it says at that instant in time, and you write that down in your record sheet on your clipboard. And the your sampling procedure is what's recommended in the appropriate ASTM methodology or other sampling methodology that you may find in the technical literature for the situation that you are dealing with. So you might, the methodology that you're using, ASTM, it might say sample the meter every 15 seconds, something like that, and do that for 20 minutes or something like that. And this will all depend on what you are, the environment that you are working in. Are you measuring sound levels of a freeway where cars are going by, or is it of a railroad line that doesn't have trains going by that frequently? So it is your sampling rate, the rate at which you read the meter, is determined by some technical guidance that you get from an ASTM standard or some other technical guidance that you come across. And then the methodology that you're using will tell you how to combine all of these readings you have taken into a single number that is an approximation of the sound that is being produced in the source room. But over the decades, this approximation has proven to be a workable way of characterizing the sound in the source room. So it's a single number that you come up with. And that is, that's your field work. Now let me get things going here. We're not going to go into speed of sound and wavelength. This comes into play when you are using things like mufflers and things like that to control sound. So we'll skip over the. Feel free, obviously, to review this material at your leisure. But a little aside now here, just to illustrate things. Loudness. What is loudness? Well, loudness is a subjective concept that characterizes how people would perceive sound changes, increases or decreases. And just to give you a feel for how people perceive loudness or changes in loudness, in this table here, if you have a sound being produced and you reduce it by 3 decibels, the acoustic energy loss, which we won't go into the calculation of, would be about 50%. And a human would perceive that as being a perceptible change. If the sound was reduced 10 decibels, there would be a 90% acoustic energy loss, and the human would perceive that sound as being half as loud as it was. And on down through the table. So that this is just how humans perceive loudness, but loudness is not a quantity that gets taken into consideration with acoustic design, noise control for buildings, zones and phones, similar vibration transmissibility. One thing that setting aside sound for a minute that is important is in the area of the vibrations. And again, vibrations are a companion of sound. And this is natural frequency. Every structural system or mechanical system has a natural frequency. And so if a forcing frequency is applied to a structural or mechanical system at or near its natural frequency, which is frequently very difficult to calculate, then resonance sets in, and the amplitude of the oscillation is increased as you approach the resonant frequency of the mechanical or structural system. And if you are right on the natural frequency and continue to apply the forcing frequency at that natural frequency, the amplitude of oscillation of the mechanical or structural system just continues to increase and increase and increase until finally the system breaks. So it's something to be avoided, and it can crop up when it's least expected resonance. So one interesting little example as far as resonant frequency is concerned. A common situation in building design is a fan room with a fan in it. And you've probably constructed the fan room out of poured in place concrete or CMU block walls and so on, so forth. And that takes care more or less of the sound. But you are concerned about vibrations being transmitted through the building structure to the occupied spaces. And a common way that the vibrations of mechanical equipment like this are controlled is to set the mechanical device, whatever it is, a fan, compressor, etc., on a frame, which you then set on spring isolators. These are like a little spring in a housing, and you put one on each corner of the supporting structure, and then you put the fan on top of that, and the fan, when it's running, it's bouncing up and down, but the bouncing is absorbed by the spring isolators and is not transmitted to the building structural elements, except if you happen to the fan happens to be running at the natural frequency of the spring isolators. Then the springs start isolating and the amplitude of their oscillation increases and increases and increases, and then can be damaged. There is a formula that has been developed, which is equation 2.7, where the natural frequency is 3.13 times the square root of 1 over SD. And SD is the static deflection of the mount, the spring loaded mounts, in inches. And so in the unloaded condition, say the spring is 2 inches long, you put the fan on it and it's compressed to 1 inch. So then the static deflection in the loaded condition is 1 inch. And you plug in that number and calculate F sum n, the natural frequency. And if the fan is running at that natural frequency, then it's hang on just a second. I need to deal with a phone call. Okay. Okay, I'm back. So this is just kind of an aside type thing, kind of an interesting little thing that you might be able to use sometime. Okay, pressing on here. This table indicates how as you get closer and closer to the natural frequency of whatever system you're dealing with, the degree of vibration isolation varies as you see it there, amplification to high isolation. So anyway, okay, now noise criteria. You've gone into the source room, you've measured the sound and you have taken your measurements and reduced them down to a single number, which is an approximation, but it has proven to be workable over many years. So that is a number that indicates the magnitude of the sound in the source room. Now, in the receiving room, you want to establish the criteria for the noise environment that you want in the receiving room. And that is dependent upon or driven by the human activity that's going on. Are people trying to sleep? Are they working at a desk doing office work? Are they working in an industrial environment? And so on and so forth. There are two numbers that have been developed over the years. One is called the room criteria, RC, and the other is the noise criteria, NC. Of these two, you'll usually be using the noise criteria. Room criteria isn't used as commonly. So noise criteria is a number that you select to represent the noise environment that you want in the receiving room. And you may supplement that noise criteria number by a speech interference level estimate. And the speech interference level, SIL, is to deal with the situation where you have two people in the receiving room and they need to talk to each other. And can they, do they need to speak in a quiet tone of voice, or do they need to speak more loudly? Do they need to shout? So on and so forth. The noise criteria and the speech interference level. The noise criteria is the primary number that you are concerned with, and it's supplemented by consideration of the speech interference level. And this table here indicates the characteristics of the noise criterion NC curves, and they range from 15 to 70. 15 is a quiet space. This would be a room, your receiving room, where people are trying to sleep. And NC 70 is a very noisy environment. This might be an industrial space, or anything over an NC 70 environment, noisier than that, is considered to be potentially harmful to people's hearing long term. So if your NC level that you select for your receiving room space is over 70, the people there are going to need to use personal protective equipment, earplugs, earmuffs, things like that. And so here, this table is the definition of the NC curves that you have available to select to define the noise environment that you consider acceptable in your receiving room. Down at the bottom is the black NC15 curve. That means that if the sound pressure at the different frequencies, and the frequencies which you see on the horizontal axis, those are within the part of the frequency spectrum that where the human ear is most sensitive. And so if, as an example, if you're at the 250 hertz level. If the sound pressure is 20 and everywhere through the frequency spectrum, your sound in the receiving room that you are selecting as your target is below that NC15, then it is said you have selected the NC15 as your target for your receiving room, and on up through the different curves until up at the top is the NC 70 curve, which is a noisy environment. So these are numbers, single numbers that you can select based on the human activity that's going on in your receiving room. And how do you go about selecting the NC number for as your target for your receiving room? Well, here is one way approach to it. This comes from the federal government, from the primarily the Department of Defense agencies, the Corps of Engineers, and Naval Facilities Engineering Command. And they have developed this table to assist in selecting the NC curves for the different spaces, depending upon what's going on in them. So like category 1, where the primary objective is sleeping, resting, relaxing. Typical spaces would be bedrooms, hospitals, so on and so forth. You would select an NC curve somewhere between 20 and 30. Category 2 is a little noisier environment, but you still want to have very good listening conditions. So this would be spaces like auditoriums, theaters, conference rooms, so on and so forth. And the recommendation is that you select a noise criterion between 15 and 30. Category 3, little noisier, but you still want to have good listening conditions. These would be private offices, classrooms, libraries, and the recommendation is that you select noise an NC curve of 30 to 35. For category 4, little noisier for fair listening conditions, though, and these might be large offices, shops, and stores. And the recommendation would be that you select an NC curve of 35 to 40. Category 5, a little noisier. You still want to have moderately fair listening conditions. So this could be lobbies, laboratories, maintenance shops. And the recommendation is that you would select an NC curve of between 40 and 50. And finally, the noisiest category is 6, kitchens, laundries, shops, garages, so on, so forth, where there's minimum acceptable speech communication, but there's no risk of hearing damage. And the recommendation here is that you would select an NC curve of 45 to 65. So depending upon whatever the human activity is that's going on, you select a single number, an NC curve, and that's your target. And so you've got the source room, the noisy room. You've taken your sound level meter in there, measured the sound level, and come up with a single number that represents the noisy room. And you have selected a single number as the target for your receiving room. And the difference between the two numbers is the sound reduction that you need to achieve by building design, the selection of the of appropriate building materials. And so if you have selected an NC30 curve as your target for your receiving room, and if the noise that's being generated in the source room is 50, then 50 minus 30 is 20. So you need to achieve a sound reduction of 20 decibels between the source room and the receiving room. Room criteria curves. Here is a table or a figure that is analogous to the NC figure that you just saw. And this is the definition of the RC curves. And we're not going to go into a discussion of them because generally speaking, in plain old ordinary building design, you will be using the NC curves. Speech interference level is a rather complex undertaking to analyze rigorously or objectively. But here in this table, you get a picture of how the noise level affects speech interference level. So if you have, as an example, two people in the receiving room who are 10 feet apart, they can communicate in a normal tone of voice if the sound level in the receiving room is 48. They would have to communicate in a raised voice if the sound level was 54 decibels, and so on through the table. And it's this just gives you a feel for speech interference levels, which may not be something that you need to concern yourself with in a lot of building design situations. Okay, now the sound distribution indoors, it's it is reduced in different ways. It's generated by a point source in the source room, and there is some reduction in the noise level by as a result of the distance between the point source and the barrier wall between the source room and the receiving room. And inside buildings, the reduction due to distance is usually pretty inconsequential because the distances in the building are not that great. They certainly come into play in the exterior environment, and you, I'm sure, have experienced this. If you're standing outside and you're talking to someone who is 5 feet away from you, there's not a lot of reduction in the sound of your voice. But if the person is a block away, he can't hear you at all. So that distance effect is quite important in the exterior environment, but usually not in buildings. A second effect that reduces the sound in a building is absorption. And this is kind of pretty much a function of the finished materials within the source room. The acoustic tiles on the ceiling, perhaps some soft wall coverings, perhaps carpet on the floor. And in general, some sound is absorbed within the source room if the finished materials are soft. And that's because the air molecules that have their vibrational energy, they impact the fibers, say, in the soft material, and the soft material deflects, absorbs some energy, and reduces the sound level just a little bit. But in the source room, the sound reductions normally in building design due to distance and absorption are very small, and you don't pay any attention to them because, among other things, they're just kind of a little freebie that you get. You get a little bit more sound reduction than you would get strictly from the barrier. And it is possible also, and we're not going to go into this, to calculate something called a room constant, which is a measure of essentially how soft the finishes are in the source room. Is there carpet on the floor? Are there acoustic tiles in the ceiling? Things like that. But usually you don't have to be too concerned about calculating the room constant. Now, let me look at my clock here and see. Yeah, we need to speed things along a little bit. We're not going to get into estimating the room constant. Here's something that is important, though, and also is not very readable, but that's just the way it goes. And when you get copies of these PowerPoints, this is readable. But these are building materials, and they are in building systems, and they the transmission loss through a given building material varies depending upon the frequency of the sound. And some building materials are better at reducing sound at low frequencies and others at high frequencies. And so the what you are basically doing is selecting a building system for the wall, as an example, or the ceiling or the floor, that gives you the best sound reduction at the frequencies of the sound that is coming from the source room. And so the sound transmission loss is the loss of sound at a given frequency for a given building material. And a system has been developed of sound where a number called a sound transmission class has been developed and implemented by test. In other words, the Chipboard people want to sell Chipboard, and so they go to an independent testing laboratory like Underwriters Laboratories, and they say, okay, here's the construction system we want to have tested. 2x6 steel studs at 16 on center with 2 layers, 5/8 chipboard both sides, and with 6-inch fiberglass blankets in the stud space. Test this. And so Underwriters Laboratories does this and tests that construction system and determines the the sound reduction at the different frequencies. And here you're seeing this is for poured in place concrete. Thicknesses ranging from 4 to 16 inches. The frequencies from 31 to 8,000, that covers the part of the frequency spectrum where the human ear is most concerned. And so as an example, an 8-inch thick concrete, poured in place concrete wall, sound at 31 hertz has a sound reduction coefficient of 34. At the 250 hertz frequency, the sound reduction is 41 dB, and on up to 5,000 or that's 8,000 hertz, the sound reduction is 61 dB. So for this material across the frequency spectrum, these are its sound reducing characteristics, ranging from, for the 8-inch thick concrete wall, ranging from 34 at the low frequencies to 61 at the high frequencies. Then a methodology has been developed and institutionalized in the ASTM standards to combine these numbers into a single number called an STC number, which has been found over decades to be a pretty good single number representation of the sound reducing characteristics of a given type of wall or floor or ceiling construction. So then you're, in a simplistic way, but it's practical in an awful lot of situations, you know the sound that is being generated in the source room is say 60 dBs, and you want to have a noise environment in the receiving room of 30 dBs. So you need to select a construction system for your barrier, 60 minus 30, or that has an STC rating of 30. So it, in many of the cases in building design, it reduces down to a simple matter of the difference between the sound that you measured in the source room and the sound that you want in the receiving room, and then selecting a construction system that will give you that reduction. And now here, I'll flip through these because we're getting a little short on time here. But here are similar test results for other building materials. Here is cinder block or lightweight concrete, dense plaster. Here the common stud type wall frames, framing walls. the three types that are defined here are type 1, 2, and 3. And so the STC values that have been assigned to these different construction systems provides a fairly simple, straightforward way to select the STC value that you need for your wall. Now, there are certain things that you can do to improve the STC value of a wall construction. One is, I'm going to flip through these expeditiously here. And the same testing has been done for window systems and door systems. So, and with a barrier wall, the STC rating that you must have for the wall, everything in that wall must have an STC rating that is at least that good. So that means the doors and windows have to have been tested and determined to have a certain STC rating. Let's see, I'm trying to get to a little further on here to there's a lot of tables here, so well, the things that you can do rather than getting into outdoor propagation, the things that you can do to improve the sound reducing characteristics of walls, barrier walls. One is to put fiberglass batts in the airspace between the studs. And that's because the airborne sound molecules impact on a microscopic scale the fibers of the fiberglass batts. The fibers deflect microscopically a certain amount, and in doing so absorb some of the acoustic energy of the air. So fiberglass batts are a good tool that you've got. Other techniques that you can use, one is flexible channels for the mounting of gypboard on the both the noisy side and the quiet side. And this is so that the you break the sound path through the solid elements in the wall. I've indicated that you're concerned primarily with airborne sound, but sound does get transmitted through the solid elements in a wall. And mounting the gypboard not directly on the studs, but on flexible channels that are attached to the studs and to the gypboard. It provides flexibility, and some of the sound is absorbed by deflection of the these flexible channels. Other techniques, double wall construction. You are the gypboard on the noisy room side is not attached to the same studs as on the quiet side, so you have broken that sound transmission path through the solid elements in the wall. Staggered studs is another approach, and the distinction between the double stud and the staggered studs is that staggered studs are the studs are on common plates and bases, And so the sound path is not broken as definitively as it is with a double stud wall construction where the studs are on separate plates and bases. Okay, this is the section on sound propagation outside, and we do not have time to go into this. But there is a reduction due to the distance effect, the distance between the source and the receiver. And in the outdoor environment, that could be quite significant. And I'm sure you can appreciate that if you're the difference between talking to someone who's 5 feet away from you and talking to someone who's 5 blocks away from you. There are other sources of attenuation, hard to quantify, and usually too transient to count on. Atmospheric effects like rain, snow, things like that. Your atmosphere is filled with these light, particularly with snow, very light particles that will deflect and absorb acoustic energy. So that's, you read about a quiet snow falling day, wind effects. Let's see, you need to review these at your leisure. And again, this is not a textbook or a design manual, but it's got some good rule of thumb type technical guidance. Landscaping, trees, if there are a lot of trees in the outside environment between the the source and the receiver, the leaves on the trees will absorb some of that acoustic energy. Airborne sound control, this is talking about things that you may need to do if you cannot develop a satisfactory solution to the noise problem with building design features. Then you have to resort to other things like mufflers and personal protective equipment. Okay, that gets us here to the end of our time. And I'm going to just kind of zip through the rest of this. Here's a quiz that you may wish to take. That brings us to the end of the line. And clearly we had a lot of material to cover today, and we could only do it very sketchily, but hopefully you got enough of a picture of what's involved in controlling noise in a building. With that, I hope that this gives you something useful moving forward, and will let you address these noise control projects as they come across your desk. And so I want to thank you very much for letting me chat with you today. And I just want to wish you all to now have a nice rest of the day. So thanks a lot. Bye.